Alright, let's go.
Hi, my name is Callie Horta, and I'm a biochemistry major from the class of 2019.
Hi everyone, I'm Raymond, and I'm a polymers chemistry student, and I'm also in the class of 2019, and today we're going to work through a little problem in our highlighted workbook, so let's go.
We will be working through problem number 3 from chapter 16.2 and the general chemistry workbook. You should begin by working on the problem yourself to see if you can get the answer. Pause the video now until you have completed the problem. Then we'll go over it together.
Alright, so the problem we'll be working on today is in chapter 16.2, and it's problem number 3, and what we're doing is we're trying to find out which we're given pairs of substances, and our goal is to determine which of the two have the higher entropy per mole of substance.
So first, we're comparing water at 200 Kelvin versus water at 298 Kelvin.
And then the next one is just hydrogen gas at 298 Kelvin and 2 atm against hydrogen gas at 298 Kelvin and 1 atm.
And then we have hydrogen gas at 298 Kelvin and 5 liters, or hydrogen gas at 298 Kelvin and 1 liter.
Next up is hydrogen gas at 500 Kelvin and 1 atm against hydrogen gas at 298 Kelvin and 1 atm.
And then water in the liquid state at 298 Kelvin, or water in the gas state at 298 Kelvin.
And then the last one is we're comparing oxygen at 298 Kelvin and 1 atm against dinitrogen tetraoxide at 298 Kelvin and 1 atm. So before we go into working through the problem, we're going to introduce pretty much what entropy is, and I guess a way to approach it so you can better prepare yourself to solve this question.
Yeah, so a lot of people define entropy as a measure of disorder, but a better way to think about it is the number of possible microstates a system can occupy. A formal equation is S, which is entropy, equals K, which is the Boltzmann constant, times the natural log of omega. And here omega is the number of possible microstates a system can occupy.
So that's the formal definition, and the formal definition is great when you need to calculate a number, but for the purpose of this question, we're more looking at different trends and just a way to predict how entropy would change if you're looking at different factors. And the 5 factors we're going to go over that this problem is going to go through is phase, temperature, molecular weight, molecular size, pressure, and volume. So how these change will change how the entropy is for this problem. And here's just a little cartoon we thought throw in for fun to show that it's not the thing you want to think about is entropy is it's about states. It's not about disorder. And so to start things off, we'll hand it off to Kelly.
So the first one that we're going to look at is temperature. We have water at 200 Kelvin versus water at 298 Kelvin. And as you can see in the diagram, on the left we have a higher temperature where there's more vibrations and rotations versus the lower temperature where there's less rotation and less states that the molecule can occupy. So you can conclude that water at 298 Kelvin will have a greater entropy than water at 200 Kelvin.
Alright, so next up we're comparing hydrogen gas at 298 Kelvin and 2 atm against hydrogen gas at 298 Kelvin and 1 atm. And so in this system, the temperatures stay the same and only pressure changes. So changing pressure compacts the molecules in the system. What that means is that it makes them more tightly together. And so you lose volume, which is closely related to pressure, and we'll go over that soon. But when you think of making the molecules more tightly together, is that there's less room for them to move. And so with that in mind, increasing your pressure would decrease that, and so higher pressure would have less entropy. So hydrogen gas at 2 atm would have higher pressure, or higher entropy.
So now we're looking at volumes effect. We have hydrogen gas at 298 Kelvin and 5 liters, or hydrogen gas at 298 Kelvin and 1 liter. So increasing the volume frees up the amount of space that a molecule can occupy. So when you have a smaller volume, you have more pressure. So it's more compact and there's not as much space. While you can see on the bottom, when you increase the volume, there will be more possible states that the molecule can occupy. So you can conclude that hydrogen gas at 5 liters will have a greater entropy than hydrogen gas at 1 liter.
So then the next example looks at hydrogen gas at 500 Kelvin and 1 atm against hydrogen gas at 298 Kelvin and 1 atm. And so there's pressure involved here, but there's no change there. And so all we're looking for is a change in temperature, and we already went over that. pretty much just to summarize it, increasing your temperature gives it more energy, more movement, more vibrations, rotations, oscillations, and so on. So a system that would have higher temperature, which is the one at 500 Kelvin, would have more entropy compared to the one at 298 Kelvin.
Now we're looking at the effect of different states. We have water in the liquid state versus water in the gas state. When you go from a solid to liquid to gas, you're increasing entropy, and that's because you are there's in the solid state it's more compact than in the liquid state, so the liquid state will have more space for the molecules to occupy, and then this also goes in the gas state. There's also more space, so they're least tightly held together and have the most space to go. So water in the gas state will have greater entropy than water in the liquid state.
All right, and so the last one is we're just comparing two different molecules. We're comparing O2 and N2O4. They're at the same conditions, same temperature, and same pressure. So all we're really looking for is the difference in the molecular size. And so in the picture on the left, we have oxygen up top, the two red, and then down on the bottom we have dinitrogen tetroxide. And so when it comes to looking at these molecules, you want to think about the bonds that are present. So for example, the oxygen only has one bond present, whereas the N2O4 has 5 different bonds. And so in terms of internal vibrations and movement, oxygen can only move through one bond, whereas N2O4 has 5 different ways of moving. So generally, having a larger molecule means you have more bonds present, and the more bonds you have present, the more internal movement that's capable. So with this in mind, the N2O4 system would have more entropy compared to the oxygen system. Always think about motion for defining entropy. So I guess just to wrap everything up, we have a quick figure right here about the different phases, and so we always want to think about motion. So the gas would have more ability to move around, whereas the solid doesn't. And the same thing goes for pressure, because decreasing your pressure makes things more compact, more tighter. So that would also result in a decrease in entropy.
So in summary, while increasing temperature, volume, and size will also increase entropy.
Yep. So that's our review.
Thanks for watching.
Thanks for watching. How do I stop this? Oh no.